All right, hey everyone. I'm not going to be there on Monday, tomorrow, so I just want to make a quick video going over some of the homework that's due this week. So the topic on WebWork 11 is mostly Riemann sums, and then a little bit of something else that we'll talk about. So, okay, what are Riemann sums? It's just approximating things. So, for example, this first problem, a car comes to a stop after 6 seconds, and then they give us this little table here on, we know the car's velocity, and we know the time. And the reason I flip it is because I want to think of velocity as y-axis and time as the x-axis. So if we look at the first column, we have 0, 82, and that's going to correspond to the point 0, 82. So that's somewhere around here. And then 242, so I'm going to label this 82, and then we go over to 2, and here's 0, and 42, that's a little bit over halfway, so maybe it's here, 242, and then we got 415, so now we're down to, I don't know, maybe about a third of that, 415, and then finally after 6 seconds, we come to a stop, 6 and 0, 6, 0. Okay, so we don't know how the car is braking. The car may have, let me actually move this over a bit if I can. Oh my goodness. There we go. All right. The car may have been braking like this. Okay. It could have been braking like this. We don't know. But we don't need to know. So we just want to approximate how far it travels with a lower bound and upper bound. Well, in this first 2 second interval, we know it began at 82 feet per second, and it ended at 42 feet per second. And so if you want a really rough lower bound, you can just pretend the car's speed was 42 feet per second the whole time. And so if you travel 42 feet per second for a total of 2 seconds, then you travel 84 feet. And then you do this on every interval. So on the next interval, we're going to take the lower of the two measurements, which is 15. So you travel 15 feet per second for 2 seconds, and that's 30 feet. And on the last interval, you've come to a complete stop, that's 0. So you'd be traveling 0 feet per second for 2 seconds, that's 0. So a very terse lower bound or coarse lower bound is 114. Whereas in upper bound, we just do the opposite. We'll just pretend the car's velocity was 82 feet per second, and then magically it became 42. And then it's 42, and magically it became 15, and it's 15, and magically it became 0. So the total distance of the red travel, well, it's this area here. So I'm going to do 82 times 2 plus 42 times 2 plus 15 times 2. So what do we get with that? I don't know. I'm going to let WebWork do it. And I highly recommend we get used to that. So there's 114. And here I have 82. And you know, all of them are times 2. So let's just go ahead and factor that 2 out. So I have 2 times 82 plus 42 plus 15. There we go. And now if we hit submit, it should... Oh, and they want units. Okay, very nice. Sure. So it traveled that many feet. And it traveled this many feet. Okay. There we go. All right. Let's do the next problem. All right. So same idea, except now they're giving us a function. And now we're starting to introduce the vocabulary words. So a Riemann sum is this idea of just pretending a function is constant on a little interval and then adding up these areas. All right, so we have some function, and it's negative x squared over 4 plus 2x, and we care about the interval from 3 to 7. Okay, fine. Does it represent anything? No, they don't give us any units. We don't know what it represents. That's fine. And they just say here's a left endpoint Riemann sum. So let me draw what they're talking about. So here's my function, and here's 3. And then how many rectangles are there? Do they say... Well, let's just count it up. We have 1, 2, 3, 4, 5, 6, 7, 8. All right, so we have 8 rectangles, and they're all going to be evenly spaced. So the way you're going to find out the width of the rectangle, so the rectangle width, is going to be the total interval length, divided by the number of rectangles. So for this problem, the total interval is from 3 to 7. So 7 minus 3 is a length of 4. And there's 8 rectangles. So 4 over 8. That means each rectangle has a length of half. So the next spot is going to be 3.5, and then 4, and so on. And I guess I'll put the 7 right here. Okay, so 3, it hits our function somewhere. 3.5, it hits our function somewhere. A left Riemann sum just means on these two lines, you're going to go to the left spot that hits your function and move over. And that's how they got this first rectangle over here. So then on the next two lines, you're going to take the left spot and move over. And that's how I got the second, and so on. So, all right, when they say what is the value of the left endpoint Riemann sum, we have to add up all of this blue area over here. So how do you do it? Well, let's figure out all the different sample spots, and for that I really should have drawn a better picture. So let's go ahead and do that now. Okay, so here's 3, 3.5, 4, 4.5, 5, 5.5, 6, 6.5, 7. Okay, great. And so all of these, we're just adding a half each time. All right, so if you look at the left Riemann sums, we use a height, which is f at 3. So we'd have to plug 3 into our function to get the height. And then the width is a half. All of these rectangles have width 1/2. So we would take f of 3, which we can compute. That's -9/4 plus 6. Okay, gross. So if you're okay with it, I'm just going to call it f of 3. But it's this number right here. Okay, so that's the height of this first rectangle. The width is 1/2. All right, that's the first area. Next area, well, it's f of 3.5, because that's going to be the next x value we care about, 3.5. That's the height of our rectangle. The width is 1/2, and that'll give us this next thing. And so you're going to continue this pattern, f of 4 times 1/2, f of 4.5 times 1/2, and so on and so on. But notice on this last rectangle here, let me zoom in a bit, this endpoint, the left endpoint is 6.5 because they all have width 1/2. So on this last rectangle, the height of my rectangle is whatever the function gives me at 6.5, which again, as a reminder, you plug in 6.5 and you get -6.5 squared over 4 plus, and I think it's 2 times 6.5, yes, which is 13. Okay, so you get whatever that number is. That's the height of this last rectangle. The area is that number times a half. So plus f of 6.5 times a half. So you'd have to do all of this, add it up, and that would be this first blank right here. Okay, I really don't want to do that. So you can use whatever technique you want, calculator, store the function, Excel. But one thing that will speed it up is notice when you do this computation, you can factor out the 1/2. There's the common width, okay? And then the heights are f of 3, f of 3.5, and on and on and on until you get to f of 6.5. And that was my left Riemann sum. So we're adding up areas, and that's the idea of a Riemann sum. So, okay, for a right Riemann sum, exact same process, but now you just use the right line. So if we have that same curve, and here's that first rectangle where the two left and right bounds happen at 3 and 3.5, well, you take the 3.5, plug it into your function, f of 3.5. That's the height for the first rectangle. And so then the area is going to be that value times the width, which is a half. So then the next one, you'd have to plug in 4 to your function, boop, boop, and that's f of 4, and then the area is that times a half. And so you just keep doing it. And so notice this time, we began with f of 3.5, and we're actually going to stop when we hit 7. That's going to be our last rectangle. And you can see that in the picture over here. So this time the computation is 1/2 times f of 3.5 plus f of 4 plus f of 4.5 plus, and you just keep going with the pattern, dot, 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 until you hit 7. So again, I don't want to do it, but that's the computation you would do to go in this next blank here. Your function may vary, your interval may vary, but in general, so my interval was 3 to 7, and my number of rectangles was 8. The way you're going to get the width of your rectangles is, so if I denote this interval as a to b, you're going to take the total interval length, which is b minus a, divided by, and this is lots of right, I'm going to call it n for number of rectangles, so we'll do n. Okay, this is going to be the common width. So how wide each of these little rectangles are. I wish I could just point with my stylus on that page. Anyway, so that's all you're going to do for the next problem, for problem 2. Problem 3 is more or less exactly like problem 1. There's just one notion that we need to talk about here, and it's a physics idea, which is that, so velocity, you can have negative velocity. We see that on the graph over here. Let me do my terrible representation of this graph. So it kind of climbs up and then goes up and down and up and down and up. Great. So here's my velocity, and here's time. And units are going to matter. So what do they use here? Feet per second and seconds. Great. So a foot per second times a second is equal to a foot. So if you multiply a velocity and a time, you get a distance. The issue is we have a non-constant velocity. My velocity at time 0 is different than my velocity at time 1 is different than my velocity at time 2, and so on. Okay. So Riemann sums are about approximating distances by just pretending your velocity is constant. So if I were to do what the picture over here is talking about, then let's switch colors real quick. Boop. I'm just going to pretend my velocity is, what is this, -3 for the entire first second, right? It's not. Like, you can see the red curve is going up, but I'm just going to pretend it's -3. And then I'm going to pretend it's -2 for the next second. Again, it's not, but we're going to do that. So if I make that assumption, then the amount of distance that I cover in this first second, well, the distance would be 3 times 1, it'd be 3 feet. But because I have negative velocity, our displacement is -3 feet. So displacement is just velocity times time. What we're used to on like an intuitive level, like if you drive at 60 miles an hour for 1 hour, you covered 60 miles. We're used to distance being speed times time. They're very similar ideas. It's just velocity takes into account whether you're traveling away or traveling towards, or traveling right or traveling left, however you want to think of it. So this is like saying we traveled 3 units to the left. And then in the next area, we approximately traveled 2 more units to the left. And then the next one, we're going to pretend we didn't travel at all. And then the next one, we're going to pretend we traveled 1 unit to the right. So now we've got 3 to the left, 2 to the left, plus nothing, plus 1 to the right. And where are we at now? This is 0, 1, 2, 3, 4. That's in the first 4 seconds. It looks like it wants the first 8 seconds. So, yeah, you're just going to go ahead and add up all these blue areas. And let's see, what does it say? It wants using the left Riemann sum, so that's the thing that's drawn, right? Again, you sort of have these 2 possible edges, and you're going to follow the leftmost edge, and that's what's going to tell you how high to go for your rectangle. Using the left Riemann sum, find approximately how far the object traveled. So that computation would go, wait, total displacement, total distance. Right. So the signed computation, where you have negative values because you're doing the velocity, that would be the first blank that we have to enter, which maybe I can actually just do that really quick. So area below the x-axis is negative, because that's when I have a negative velocity. So I'd have -3 minus 1, and then it looks like I have plus 1. I'm literally just adding up these blue areas, 1, 2, 3, 4, and then 1, and then 2 more is 7, and then 4 more is 11, and then we get up to 12. Okay, great. Oops. Plus 12. So if I hit submit, it should like that. Oh, it probably wants units, of course, of course. Okay, so I suspect we have to put the whole thing in parentheses. That way it knows this whole thing is talking about feet. And let's see, submit answer. Incorrect. Oh, it did this. Let's see. Using the left hand pointer, to find approximately how far the object traveled. Your answer must include correct units. Okay. Data might look like this. Okay. And the units are feet per second and seconds. Okay. So -3. Right here. There should be a -2. Sorry, looking at this picture, you can see in the first column there's 3 blue squares. That's because I did -3 times 1. In the next column, there's 2 blue squares, and I, for whatever reason, wrote -1. So now let's submit. Now it's correct. We all make mistakes. Okay, so that's the displacement. That's going to be the same for both problems. It's just a matter of whether you do a left or right Riemann sum. Now, total distance traveled. Okay, so how is speed related to velocity? Well, speed is the absolute value of the velocity. So absolute value. So for example, these first 2 numbers, I have -3 and -2. And that's because my velocity was -3 feet per second for the entire second. So I covered -3 feet, meaning I traveled 3 feet to the left. But my speed is the absolute value of this. So I would do absolute value of -3 plus absolute value of -2 plus. And you just keep doing the absolute value of the velocity at each spot. So in this case, you could just change it to 3 plus 2 plus 1 plus 12, or you can just add it all up. And what is that? 6 plus 12 is 18 feet. Submit answer. And there you go. So again, the only difference between the first problem, the first part of this problem and the second is whether you do left or right Riemann sum. Velocity, you can travel left or right, and so that corresponds to having signed area. We sort of say the area below the x-axis is negative, and the area above the x-axis is positive, and then you add them all up to get some sort of net area. So, okay, what's the next question? Right, so again, these are Riemann sums. I suppose we can do, let's see what the next one looks like. Now we're getting these things. All right, so relating all of this, we'll do in class a bit more next time, but let's just skip to problem 5 to start to get at what's happening. So, what we're going to be looking at are these things called definite integrals, and here's an example of one. So the integral from 4 to 5 of e to the x. That's how we would say this in words. And what that corresponds to, so if I were to graph the e to the x function, looks like this. And way over here from 4 to 5, there's some area underneath this curve. Some area. Okay? Do you know the exact area? If you haven't had calculus, you probably don't. And that area is what this expression is talking about. Okay? And more importantly, it's a signed area. So this is a positive area because it's above the x-axis. But if you had a function like, for example, sine of x, it goes like this, right? Then above would be positive area, and below would be negative area. So anyway, this idea of what's an area under curve, that's a hard problem, right? And so what you could do to just kind of approximate it, and this is no surprise, is you could just chop it up into a lot of little pieces and then just pretend each piece is a rectangle. And as you do more and more pieces, right, if these were skinnier and skinnier, then I'll get a better and better approximation, and you can try and figure out what it is. And that's the whole idea behind Riemann sums, is we're just going to do approximations. And we're not even going to do very good ones. So in this problem, it says a left Riemann sum with n equals 2 rectangles. So I need to draw 2 equally spaced rectangles in between 4 and 5. And so I take the midpoint. You can always, there's different ways to do it. You could find the width by finding the width of your whole interval. So right minus left, divided by your number of rectangles, you'll get a half. And that tells you how much to move over. So this would be 4 plus a half. So Right, this half is that half. All right, so now if I come up here, I'm going to hit my curve at, so this will be e to the 4.5. This value here is e to the 4, and this value over here is e to the 5. Okay, I want the left Riemann sum. So I'm going to look between, can I get, no, not that. What do I want? We'll just go ahead and expand this. Great. I'm going to look between these first two lines here, and I'm going to take the line on the left to tell me what the height of my rectangle is. So let's go ahead and draw that in. Line on the left, draw the height. Okay, so what is this, the area of this first rectangle? Well, its height is e to the 4, and its width is 1/2. So there's the area. All right, and now I have this next rectangle where it's between these two vertical lines. I want a left Riemann sum, so I take the line on the left. That tells me my height. I move it over. Here's my rectangle. What's the area of this rectangle? It's e to the 4.5 times 1/2. So my total area is what I get when I add those together. Let's hop over here. My sum is e to the 4 times 1/2, which I'll just do divided by 2. And then e to the 4.5, and again, I'll just say divided by 2. So, should like that. Let's see. Yep, there we go. On another sketch, write out the terms for the sums you don't evaluate. For the right Riemann sum, so if you did the exact same process, then the right Riemann sum, when I look at these two vertical lines, I take the one on the right. So now the height of that first rectangle is e to the 4.5. Similarly, for the next rectangle, I take the one on the right, and its height is e to the 5. So it's the exact same process, but now I have e to the 4.5. That's divided by 2, and here is e to the 5, and that's divided by 2. And then based on the picture, you can see which is an overestimate, which is an underestimate. The left was an underestimate, and the right was an overestimate, and that depends on the shape of your graph. Okay, so if I hit submit, they're all correct. That's all we're looking for there. I think we're almost out of the Riemann sum ones. Find the exact distance. Okay, so now here's the whole idea where we're headed with the interpretation. This will be the last problem I do, and then we can just flesh out all the details in class sometime. All right, so velocity of a car is given by f of t is equal to 6t meters per second. Use the graph to find the exact distance traveled by the car from 0 to 10 seconds. Okay, so here's the idea. So the velocity of the car is given by 6t, and I'm going to go from 0 to 10. And it turns out that this area is the distance. Technically, it's the displacement, because I'm talking about velocity, but if your velocity is positive, which it is, we're above the x-axis, then velocity and speed are the same thing, and so we can just talk about distance. So no longer is distance velocity times time, because velocity is changing. Instead, we're going to integrate the velocity function with respect to time, okay? And these symbols, let me write this out a little bit more. So we have 0 to 10. This tells me my bounds, my time bounds. This little dt is telling me that it's with respect to time. My function is 6t. What all this collection of symbols means is the area underneath this function, so underneath 6t, between 0 and 10. 0 and 10, underneath the function, that area. And this is just a triangle. The height of this triangle is 60, right, if you plug in 10. So 1/2 base times height. That's 300. And what we're going to get to eventually is the fundamental theorem of calculus. So remember when we just had these symbols, this happened just before break. What that means is we want to find a function where if you take its derivative, you get the function inside your integral, so 6t. So can we think of a function whose derivative is 6t? Well, I can, yeah. But we can do the power rule. So this is 1, we're going to make it a 2 and divide by 2. And that 6 comes along for the ride. But 6 over 2 can cancel, and we get 3t squared. Okay, so this is an antiderivative for 6t. 3t squared is an antiderivative for 6t. What we're going to find out is the reason we use all these symbols is if you have this function, so 3t squared, in math, we tend to put these little values at the top and the bottom to mean evaluation. And when you have this vertical line with it, it means you evaluated the top number, so 3 times 10 squared, minus evaluating the bottom number, 3 times 0 squared. And what is this? That's 3 times 100. And hey, look at that, we got 300 yet again. So this is where we're headed in the class. Let me just put this in and does it say include units? It sure does. And this is in meters. So we're going to do nope, not that, 300 meters, and hit submit, and there it is. Okay, I'll see you in class later this week.